Have you ever wondered how the internet sends massive amounts of data across the globe in an instant? Or how scientists build clocks so accurate they won't lose a second in billions of years? The secret is light. For decades, we've been getting better and better at controlling light, creating a multi-billion-dollar industry that powers everything from data centers to cutting-edge science. But one huge challenge has remained shrinking powerful light sources down to the size of a computer chip. Imagine a tiny chip that could take a single color laser light and transform it into a whole rainbow of new colors. This isn't just a cool party trick. It's a critical component for building next-generation quantum computers and making ultra-precise measurements of time and frequency. For years, researchers have tried to build such a device, but it's been incredibly difficult. Now, a team at the Joint Quantum Institute has made a massive breakthrough. They've designed and built new chips that can reliably convert one color of light into a trio of new hues. And they do it automatically, without any of the painstaking adjustments that plagued previous attempts. This could be a game changer for the future of technology. So how do these chips work their magic? They're what we call photonic devices, which are like tiny highways for photons. The fundamental particles of light. Just like electronic chips control the flow of electrons, photonic chips can split, route, and manipulate streams of photons. One of the researchers, Mohamed Afesi, explains that a major hurdle for on-chip light sources has been their lack of versatility and reproducibility. You could design a perfect chip on paper, but tiny manufacturing imperfections would mean only a few of them actually worked in reality. His team's work is a huge step towards solving this problem. Now, these new chips are much more than a simple prism. A prism just paints existing colors in white light. These chips actually create brand new colors that weren't there to begin with. This is a huge deal. It saves space and energy by eliminating the need for extra lasers on a chip, and in many cases, lasers that produce these specific new colors don't even exist. To make new colors, you need something called a nonlinear interaction. Normally, when light passes through a material, its color or frequency doesn't change. But if you concentrate the light intensely enough, it can actually change the properties of the material it's passing through, which in turn changes the light itself. This feedback loop can generate a whole spectrum of different frequencies. The problem is, these nonlinear interactions are usually incredibly weak. The very first time one was observed back in 1961, the signal was so faint that the publisher thought it was just as much unhelpful and erased it from the final paper. The smash was the first evidence of a process called second harmonic generation, where two photons of one color combine to create a single photon with double the frequency. Since then, scientists have found clever ways to boost these effects. One popular method is using something called a photonic resonator. Think of it like a tiny racetrack for light. These resonators are engineered to guide light in tight circles, forcing it to circulate hundreds of thousands or even millions of times before it's released. Each repeats a little bit of a nonlinear effect, and all those leaps together create a much stronger one. But even with resonators, there's a catch. Let's say you want to double the frequency of your light. First, your resonator has to be the perfect size and shape to support both the original frequency and the new double frequency. It's like a guitar string that can only vibrate at specific notes, but that's not all. You also have to ensure that both colors of light travel around the racetrack at the exact same speed. If they don't, they'll fall out of sync, and the color changing process becomes super inefficient. Getting both of these conditions, the frequency matching and the phase matching perfect at the same time, is extremely difficult. It is like trying to see a solar eclipse. The sun and moon have to align perfectly. Even the world's best manufacturing processes can make every chip identical. Tiny nanometer scale differences from one chip to the next are enough to throw off this perfect alignment, rendering most of the chips unaware useless. One solution is to build tiny heaters onto the chips to actively tune them. But this adds complexity and requires extra power. It's a clunky workaround for a fundamental problem. This is where the new breakthrough really shines. their research team discovered a brilliant way to bypass this entire issue. Their design uses an array of hundreds of microscopic ring resonators all working together, like circulates weakly on each tiny ring. But it also travels more slowly on the edge of the entire array. Like a super ring, this design creates two different time scales for the light, and setting realize this structure as an incredible side effect. It initially creates multiple opportunities for the frequency and phase matching conditions to be met. All on its own, they didn't have to meticulously engineer it or hit it, as one of the leaders, Mahmoud Jalalimerabad, put it. The two time scales essentially provide the perfect alignment for free. They tested 6 different chips made from the same wafer, shining a standard telecom frequency LASR them. And to their delight, every single one worked. They all took the invisible infrared light and generated brilliant red, green, and blue light, the second, third, and fourth harmonics. For comparison, they also tested standard single ring devices with built-in heaters. Even with active tuning, only one of the 3 single ring chips managed to produce just a second harmonic, and only within a very narrow range of settings. The ultimate scale is, on the other hand, work flawlessly with no tuning at all and across a much broader range of input frequencies. They even found that as they cranked up the laser's intensity, the chip started producing even more colored sound each harmonic, creating a beautiful nested frequency cone, a vital tool for precision measurement. Mahmoud Jalalimerabad summed it up perfectly: we don't need heaters. We don't have heaters, they just work. It addresses a long-standing problem. This innovation could have massive implications for any field that uses integrated photonics. From scientific measurement and frequency convection to nonlinear optical computing, be creating a reliable, passive way to generate multiple colors on a chip. This research removes a major roadblock and paves the way for more powerful and versatile light-based technologies. We are one step closer to a future where the power of a rainbow can be harnessed on a single tiny chip. What do you think this technology will enable next? Let me know in the comments below. Thanks for watching. And don't forget to subscribe for more amazing science breakthroughs.